Hey everybody, happy Wednesday. I am so grateful that I was able to be there on Monday, that we were able to go through some things. Hopefully these rectangle approximations for areas make a little more sense. I did receive at least one request to go through a homework problem, problem number 52, so I'm going to do that here on the board as we start off class here. And then the plan for today, obviously we don't have class tomorrow, that's kind of switched up. We're actually starting a new section, but the section is really a continuation of what we were talking about previously. So we'll look at doing some rectangle stuff in a little more generality, but I do need to say a few things kind of regarding that. But we've kind of reached, this has been kind of the most difficult part of the material. So we get past this and we're kind of rolling downhill, I think, in a good way. So let's go ahead and do section 4.2, number 52. Okay. So I believe, let me just check and make sure, because it would be really bad if I did the wrong problem here. All right, so y equals 1 minus x squared, and we're from -1 to 1. Okay. And 1 minus x squared, I think we've talked about this before. You don't actually have to, you could just kind of go, and it really doesn't matter what you end up getting the function to look like. In this case, I'm actually going to show you the function looks like this, from -1 to 1. You don't have to have drawn that. It's not a big deal. Okay, so we are going to approximate this. So it says, use the limit process to find the area of the region between the graph of the function and the x-axis over the indicated interval. Okay, so when it says find area using a limiting process, or find area as the limit of rectangles, we have kind of our standard 4 or 5 steps. Okay, the first thing that we're going to do is we're going to draw in the subintervals. We're going to cut up the interval into equal pieces. Okay, so we're going to do n intervals. Now we don't technically know how big n is, so we're just going to kind of mark off some things there. And then we're going to, and the width, which we call delta x. In this case, the whole thing is length 2. So our width is going to be 2 over n of each of those rectangles. All right, second thing we do is we draw in the rectangles. Okay, we're using right endpoints. Okay, so and you don't have to do all of them, we're just going to do a few. So now let's calculate the area sum, the sum of the rectangles. Okay, and these are right endpoints and n rectangles, that's why we use r sub n. So let's start with this first rectangle here. The width of the rectangle is 2 over n. That's the easy part. And then the height is what we get when we plug this point right here into the function. Now, this point right here, I know this might be a little small to see. This point right here is -1, and then I'm going over 2 over n. So this is -1 plus 2 over n. Is that point right there. So what we're going to do is we're going to take this function, 1 minus x squared, and we're plugging in that point, -1 plus 2 over n. Got it? That's our first rectangle. Okay. All right, next rectangle has width 2 over n, and the height, we're going to plug again into that function 1 minus x squared. but we're going to plug in this point, and this point is -1 plus 2 copies of 2 over n. Okay, I started at -1 and I went over 2 copies of 2 over n. So it's -1 plus 2 copies of 2 over n. Got it? And looking at the pattern, we kind of see, okay, the next one's going to be 2 over n times the quantity 1 minus something squared, and that something is -1 plus 3 copies of 2 over n, right? And we keep going dot, 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 until we get to n copies of 2 over n. Got it? So that is our area sum. And now what we're going to do is we're going to stick it in sigma notation and then play with it until we get a nice closed form. Once we get that closed form, then the last step is going to be take that limit. Okay? So it is a sum, and the thing that's consistent in all of this, we have 2 over n times 1 minus something squared, and that something is -1 plus something times 2 over n, so I'm going to call that I. And I starts at 1, then goes to 2, then goes to 3, all the way up to n. So that should be your formula in sigma notation. We good? All right. So now we are going to try to simplify this sum, so I'm going to need to multiply that stuff out. So I'm going to FOIL -1 plus 2i over n times -1 plus 2i over n, right? That's what this thing squared. So I'm going to get -1 times -1 is 1, minus 2i over n, minus 2i over n is minus 4i over n. Okay, and then the last term is plus 4i squared over n squared. All right. We're good? Simplifying further. 1 minus 1 is 0, and then I just have to stick that negative on the other two things. So I've got -4i over n. Sorry, the negative is positive 4i over n, and then I've got a -4i squared over n squared. All right. And then, if we simplify even further, multiply that 2 over n in, I get 8i over n squared minus 8i squared over n cubed. All right. Now, what should we do next? We're going to separate these, and hope I'm not jumping the gun here, but I'm actually going to separate them and pull out all the constants. So the constants in this first one are 8 over n squared, and then I have an I left, minus, in this one I've got an 8 over n cubed, and then what's left here is an I squared. That clear so far? So I separated these two, and then I pulled the constants out from here and constants out from here. The only thing that's not constant is I, or I squared. All right, and we've got a formula for the sum of 1 through n, and then the sum of 1 squared through n squared. So those formulas are, so let's leave the 8 over n squared there. The sum of I is going to be n times n plus 1 over 2. And then minus the other term there. And I've got the sum of I squared is going to be n times n plus 1 times 2n plus 1 all over 6. So that's at least a lot better formula than it doesn't involve any sigma notation. Now let's clean this up a little bit. I can cancel one of the n's here. Oops. And the 2 cancels into the 8. So I've got 4 times n plus 1 over n. This should look familiar. That thing keeps going to 1, right? That's what we saw in class before. So this term is eventually going to go to 4. You can kind of tell that. Minus, okay? So now I can cancel a 2 in both of these. So I've got a 4 left here and a 3 left here. And one of the n's. So I've got, if I pull the constants out, I've got 4/3. And on the top, I've got n plus 1 times 2n plus 1 over n squared. Are we good to go? Okay. Let me do one more step before we take a limit. N plus 1 over n. Again, this is going to go to 1. Let's multiply this out here. I've got 2n squared plus 2n plus n is 3n plus 1 all over n squared. Okay, so technically this first term, if I divided both things by n, it's 1 plus 1 over n. This term right here is 2n squared over n squared is 2, plus 3n over n squared is 3 over n, plus 1 over n squared. Excuse me. I'm allergic to big calculations. No, I'm kidding. Okay, so now we let n go to infinity, so the limit, make sure you guys can see this, as n goes to infinity of these rectangles is the limit as n goes to infinity of this thing right here. And so the first part obviously goes to 4. Can you see that? My head's in the way. Minus, the second part is 4/3, and then this thing, these terms go to 0, so the only thing left there is 2. So I've got here 4 minus 8/3. 4 is 12/3, so this is just 4/3 here. That is my area. 4/3. Got it? All right. So really the calculus part, I think the sticking points tend to be putting stuff in sigma notation, and there's a bunch of simplifying that happens, sticking in for those two formulas, and then getting it to a place where we can take a limit pretty easily. Okay? All right, pardon me, I'm just going to blow my nose here. Okay, so I think now that we've done that, let's jump into the next section again, which is a kind of a continuation of what we're doing here, but we're going to do it in a little bit more generality, but not really that much. Okay? All right. So now we're jumping into section 4.3, which is again a continuation of areas under curves, but this is called Riemann sums and definite integrals. And I'm going to give you definitions for both of those things. So they're not really new concepts, but we just need to kind of bring together everything that we've done to kind of put this in one place, okay? So now in general, our task that's ahead of us is that we want to find the area under a function f of x from a to b. That's our task. Okay, so that area looks like, so it's the area between the function and the x-axis. So this is area between f and the x-axis. Okay, for now I'll call that area A. So following our methodology, what we're going to do is we're going to start, we're going to do the same thing that we did before. Our first step is going to be break the interval into n equal pieces. Okay. All right, so I'm going to do this here. Now, one thing that's going to be a little bit different here is I'm actually going to label these pieces here. Okay, so I'm going to call this, I'm going to call A, I'm going to give it a new name, I'm going to call it x0. And then this first, after A, the first tick right there is going to be x1, then x2, then x3, x4, and then the last one, which is B, is going to be x sub n. Now all I'm doing is just giving these interval slices, I'm just giving them names. x0 is the first slice, which happens to be the endpoint A. Then x1, then x2, then x3, all the way up to the last one, which is going to be x sub n. Okay? Now the width is going to be the width of the whole thing, the width of each rectangle, which we're still calling delta x, is the width of the whole thing. Now, if this is A and this is B, and we're doing this in general, if this was like 2 and 5, the width would be 3, right? So if this is A and this is B, the width of the whole thing is going to be B minus A. But we're cutting that into n equal pieces, so it's going to be B minus A over n. Got it? Okay. So it's basically the same thing that we did before. We're cutting it into n equal pieces. All I did was label the endpoints. So that's the first step. Second step is I want to pick points x1 star, x2 star, x3 star, up to xn star in the intervals where I'll take the rectangle heights, okay? What I mean by this, so let me just let you write that down for a second. So I'm going to pick points x1, x2, x1 star, x2 star, x3 star, all the way up to xn star, in the intervals where I'm going to take the heights of the rectangles. Okay? What I mean by that is that what we've done up to this point is we've always used the right endpoint. And I've told you, when I have you actually do these calculations, you'll always use the right endpoint. And I'm not going back on my word there. But the point here is that we don't always have to use the right endpoint. So if here's my function, and let's say I'm in the interval from x3 to x4, okay, I've got an x2 here, I've got an x5 here, okay, but I'm just focusing on one interval here, from x3 right here to x4. I need to pick a point in here where I'm going to take the height. Now, usually what we've done is we've taken the right endpoint. But you don't have to take the right endpoint. You could take the left endpoint, you could take the middle, the midpoint, you could take some other random point. You could take the highest point, you could take the lowest point. So the point is, at some place in this interval, and it could be one endpoint or the other, we're going to pick a point that I'm going to call, in this case, x sub 4 star. And wherever the function is right there, that's where I'm going to take my height for that specific individual rectangle. Now I've got n of these, so I'm going to have an x1 star in the first interval here, an x2 star in the second interval, an x3 star in the third interval. So I'm just going to have, there's a place where for each one of these I'm going to pick a height, right? That make sense? Okay. And then I'm going to draw in the rectangles that correspond to that height. So maybe kind of extrapolating over here, let me do this. Sorry, I'm going to kind of run into my explanation a little bit. But let's say, here's the first, here's A, which is x0. So in the first interval, I'm going to pick a place. Let's call it, let's say I pick this point right over here, and I'm going to call that x1 star. And that's where I'm going to take the height of the rectangle for that first rectangle. And then over here, let's say I pick this point over here for the second. I'm going to call that x2 star. So I'm going to take the height right there. And for this third interval, right here, I'm going to pick x3 star. Let's just pick it to be right in the middle. Okay, so then I'm going to take the height right there. So the point is, you could pick right endpoints, you could pick left endpoints, you could just pick random points in how this generally works. Okay? Got it? All right. So now our next step is going to be to add up the areas of the rectangles. Okay, now we're doing this in general, but I want you to see kind of where this comes from. So the first rectangle has width delta x, right? And I'm just going to leave it as delta x because I'm doing this in general and I don't want to make it super complicated. So the first rectangle has width delta x, and the height we're taking at this point that we picked, x1 star, and we're plugging it in the function. So we get a height of f of x1 star. It's what we get when we stick this point into the function. Okay? Okay, second rectangle. The width is delta x, and the height is what we get when we stick the second point that we selected into the function. So it's going to be f of that point, which in this case we labeled x2 star. Okay. What about the third rectangle? What is going to be the formula for that area? Delta x is our width. The height is going to be f of x3 star, right? Okay, and then we're going to get, the last one's going to be delta x times f of x of n star. Okay, got it? So those are the areas of our rectangles. Now this is super general. You wouldn't actually be able to take a limit here. You would need to pick the points, but this is just to sort of represent how this works in general. Let's go ahead and put this in sigma notation. So we've got the sum. Everything has a delta x and an f of x sub something star, and that something starts at 1 and goes up to n. Okay, so every rectangle I've got a width and a height. Now, for reasons that you're going to see in a minute, I'm actually just going to switch the order of these, the width and the height. So I've got height times width. This is my height, and this is my width. Okay? So this is my sum of the areas of rectangles. So this thing right here, the sum of the areas of rectangles, this is what we call a Riemann sum. Okay, sum of areas of rectangles that are approximating the area under the function. This is named after a mathematician named Riemann, this is very general. Now the book actually presents an even more general version of this. I'm going to talk about that in a second. But we call this sum a Riemann sum, and all that it means is it's a sum of areas of rectangles that are approximating our area under the function. Okay. Now, what's our last step? Okay, our last step is that we let n go to infinity. Okay. Now, this is where we should pause and we should be very, very careful. You know that from our experience of taking limits, many times you can take a limit and you don't actually get a limit. In all the problems that I've shown you up to this point, you actually do get a limit. But there's nothing to say that we shouldn't, at some point, something goes like totally wacko and the area of rectangles goes to infinity or oscillates up and down or does weird things, right? There's nothing that tells us that actually needs to have a limit. Now, I'm going to present here a theorem that I'm not going to prove at all because it involves some mathematics that we are not yet prepared to really tackle. If you pursue a degree in math, then you will be able to tackle it. But here's what this theorem says. Okay. So if there's a special case when we know this limit always exists. Okay, so if f is continuous, you see a theme here? F is continuous on the closed interval from a to b. We've seen that a lot, right? We've got a nice continuous function, no crazy breaks. And x1 star, x2 star, all the way up to xn star are any points in the subintervals. So in other words, it doesn't matter if you pick right endpoints or left endpoints or midpoints or highest points or lowest points. None of that matters. Okay, if the function is continuous on the closed interval, then the limit as n goes to infinity of that sum of height times width always exists. I'm going to put a big exclamation point right there. That limit always exists. Okay? So as long as we're talking about a continuous function, if you were able to take that limit, now we've only been able to take it in very special cases, but if you were able to take that limit, then that limit will always exist. Okay? So here's where here is where I want to give a definition now. This is the other term. Let's see if I can fit it in here. List it. All right, so let's put a definition here. Because I'd like to have this picture to still be able to talk about, okay? So in this case, when f is continuous, then the area between f and the x-axis is the limit as n goes to infinity of this sum, okay, height times width, and I'm hoping you can see that. Okay. The area between the function and the x-axis actually is that limit, and we're going to give that a very special terminology. We're going to give it a name. Now, in order to understand this, remember that when we had derivatives, we took a slope, which was the change in y or the change in x, and then when we took a limit, remember when we take limits, I mentioned this before, when we take limits, and to notate that we took a limit, we generally take Greek letters and turn them into Roman letters. So we have a delta here, which is a Greek letter, and it stands for the Roman letter D. So my delta y turns into a dy, and my delta x turns into a dx. So that's why one of the reasons why we refer to the derivative as dy over dx. It comes from the change in y over change in x. It comes from the slope of the secant line, right? So we're going to do that same thing down here. When we take this limit, what we're going to do is we're going to change the delta x into a dx. We're going to change the sigma, which is the Greek for the Roman letter s, into an s, but it's going to be an elongated one. We're going to keep this notation of the function itself. We're going to write f of x here. And then we're going to write the endpoints of the interval on the bottom and the top of this thing right there. Okay? So this notation is going to be our notation for the area between the function and the x-axis. Okay? So let me, now it's probably not possible for me to write anymore. So we're going to call that, I can at least fit a little bit on here. We're going to call this the definite integral. And all that definite integral means is it's the area between the function and the x-axis from one point to another. Okay? So, all right, so the definite integral of f from a to b, we notate as the integral, it's elongated s, from a to b, of f of x dx. That's how we read this, okay? The a is known as the lower limit of integration. The b is known as the upper limit. And then the thing inside, the height, is known as the integrand. Okay. But all this notation stands for is this area right here, the area between the function and the x-axis. Okay, and it turns out it's the limit of rectangles, the limit of areas of rectangles, but that is the nice closed form for writing that area. Okay, so let's look at a couple of examples here. All right. Okay, so for example, let's take the function e to the x from 0 to 1. So let me draw this just for a second. So remember, e to the x goes like this, and I'm going from 0 to 1. So the area that I'm interested in is this area right here. Okay. The way that I symbolize that area is it's the area, we're going to use an S for that, from 0 to 1 of this function. And the way that we think of it is it's the limit of a sum of rectangles where this is the height and this is the width. Does that make sense? So this notation just means that area right there. The area between the function and the x-axis between 0 and 1. Now, if I were to try to calculate this, what I would have to do is that step-by-step process that we were talking about before. So, for example, I would have to cut up my interval into n pieces, just like we were doing before. The widths would be, in this case, 1 over n, right? And then the sum, if I were to use right endpoints, the first rectangle, if I draw these rectangles in, the first rectangle would have width 1 over n, and the height is what I get when I plug this point, which is 1 over n, into the function, so it would be e to the 1 over n. The second rectangle has width 1 over n, and height what I get when I plug the second point into the function, which in this case is e to the 2 over n. Next one's going to be 1 over n, e to the 3 over n, right? Okay. Then all the way up to 1 over n, e to the n over n, e to the 1, which makes sense, that's our last point. So in sigma notation, that's going to be 1 over n, e to the I over n. Now the problem is that we don't have a nice formula for this. I can pull the constants out, right? 1 over n, anything that's multiplied as a constant, I can pull it out. But this e to the I over n, I do not know a nice formula for that sum right there. We have the sum of I, the sum of I squared, the sum of constants. We do not have a formula for this. But if I could get a formula for this, and then take a limit, the limit of this, we know that that function is continuous, so we know that this limit actually exists, but I have no idea how to calculate it right now. So we know this limit exists, and we call that the area under e to the x from 0 to 1. Does that make sense? Okay. So that's all that notation means. Let me show you one more example. Okay, if we were to take the function sine from 0 to 2 pi. Okay, so here's the sine function from 0 to 2 pi, and I want this area right there. So the area is defined to be the limit of the sum of rectangles with height and width, sum of the areas of rectangles, height times width. But the way that we write that area is it's the area from 0 to 2 pi of between the sine function and the x-axis. So we would write that area as the integral from 0 to 2 pi of sine x dx. We don't have any nice way to calculate this limit right now. We will next week. We'll have a really nice way to calculate this without having any limits at all. It's going to be super nice. But for now, what I want you to get used to is just this notation for the area. The area between the function and the x-axis is notated this way. Notated this way. Got it? Okay. Couple things that I want to note here. First of all, you only need to use the limit. You only need to use the limit weight method of calculating these areas if it says evaluate the definite integral by the limit definition. Okay, the limit definition is using rectangles, limit of rectangles. Okay, so number one, kind of like if you remember when we did derivatives, if I say use the definition of the derivative, you have to do a limit. In the same way, if I say use the definition of the definite integral or use the limit definition of the definite integral to calculate this area, you have to do You have to do this step-by-step process. You have to cut it up into n pieces, draw the rectangles, write down the areas, get it into sigma notation, and then take a limit. If it doesn't say that, then you don't have to do it that way. And there's going to be other methods that we're going to have moving forward for how to do these various calculations. Okay, we will have different methods for how to do these calculations. But for now, we are stuck. If we can do the limit, then we're stuck. We're stuck doing that. So that's the first note. The second note is that the book really tries to get fancy here, and there's a much more general way that you can do this. You don't, for instance, the intervals don't all have to be the same width. That stuff starts to get really complicated, and we're not going to go down that road. When you first run into Riemann sums, when you first run into using rectangles to approximate area, it's best to just think of using equal width, and we will do this all the time with equal width rectangles. It doesn't have to be equal width, but we won't get into what happens when it's not equal width. Okay. My last note, I'll hold off on that note until Monday, I think. Okay, so obviously there's no quiz tomorrow. You have some homework that is due on Monday, and you've got the sheet that kind of shows that. A couple of those are limit definition. I think you've got 4 of those: number 3, number 4, number 6, and number 7 on section 4.3. So this right here is an opportunity for you to work on those. Okay. Let me just make one note here, kind of as an example. Another one that's on your homework is like number 18. Okay, what number 18, if you open to section 4.3 and take a look at number 18, it says set up the definite integral that yields the area of the region. Do not evaluate the integral. Okay, what they want you to do there, this is not supposed to be super complicated. They don't want you to, so we're going, this is the function, and we want to go from -1 to 1. All that they want you to do is practice writing these notations here. So this would be the area from -1 to 1 underneath this function, height times width. Right? That's all they want you to do on that problem. It's not supposed to be super complicated. Okay, they're not asking here to graph it, cut up rectangles, do all that stuff. They're not asking you to do that. So for 15, 18, and 19, all you need to do is set up the actual the definite integral. Okay, I think that's it. And so tomorrow you've got a normal Friday, and we'll see you back on Monday. Have a great weekend.